Hello everyone and welcome back to yet another video on the series Physics, Light, Reflection and Refraction. And today we will be continuing the chapter and taking up the next topic, that is spherical mirrors. Now we've already looked at plane mirrors in the last video and we've discussed how plane mirrors work, what kind of images plane mirrors form, right? And in this video we will be looking at spherical mirrors and their properties and the two main kinds of spherical mirrors. Now, as I've discussed in the video on reflection, spherical mirrors are basically those mirrors that are derived from a reflecting sphere, right? That are derived from a reflecting sphere. Now, the reflecting part of the sphere may be inner part of the sphere or outer part of the sphere, right? But irrespective of that, there are some features which we need to understand, right? So suppose this is my reflecting sphere. Right, this is my reflecting sphere. Now, the radius of this sphere, okay, you can see that there is a radius of the sphere, r, right? This is the radius of the sphere, and let me name the point, the center of the sphere as C, capital C, and this length has some small r, or better say, not small r, capital R. So the center of the sphere is denoted by capital R, capital C, and the radius of the sphere is denoted by capital R. The center of this reflecting sphere, right? The center of this reflecting sphere is called the center of curvature. Okay, it is called the center of curvature, right? The center of this reflecting sphere. Now, it may be of two kinds. We're going to discuss that later. But the center of this reflecting sphere, whether inner reflecting surface or outer reflecting surface, irrespective of that, it is called the center of curvature. And the radius of the sphere, right? This radius, capital R, is called the radius of curvature. Is called the radius of curvature, right? So that's with this. Now, radius of curvature. Now the midpoint, leave that, yeah. The midpoint, or leave that, let's just leave that because it's different. So this is the basic thing you need to understand, right? The radius of curvature and the center of curvature, right? Now, depending on the kind of reflecting surface there are two kinds of spherical mirrors. So there can be a reflecting surface which is an outer reflecting surface. That is, this outer surface is non-reflecting and the inner surface is reflecting. So they can be an inner reflecting surface. Right, so these lines denote that this outer surface is non-reflecting. So this surface is non-reflecting. Right, it is a non-reflecting surface. And this inner surface, which is, smooth, this surface is the reflecting surface. Okay, this is the reflecting surface. Now, suppose I cut out one part of this mirror. So suppose I'm cutting out some part of this mirror. Okay, this is my part. Okay, so this is my mirror, which I've cut out. And let's just take this mirror out now. So suppose this is my mirror. Okay, it's not correct. Right, so this is the part of the mirror, that part of the sphere I removed. Now you can see that here this inner surface is reflecting and it is cave shaped, right? This cave shaped. And then this outer surface of the sphere is non-reflecting. So a light ray can strike here and it can reflect, right? A light ray can strike here and reflect. So these are some basic things which happen. This is the reflecting surface, right? This mirror, which is obtained from a sphere of, where the outer surface is non-reflecting and the inner surface is reflecting, is known as a concave mirror. Right? Is known as a concave mirror, right? Now, if you take out the center of curvature of this mirror, right? So you can draw this mirror with a proper center of curvature and a proper radius of curvature also. So suppose I have a concave mirror. Right, this is my concave mirror. And this is the imaginary line which I take. Okay, there is an imaginary line we take in case of mirrors, and that is called the principal axis. Okay, this mirror, this line, this imaginary line is called the principal axis. Okay, it is there in both convex and concave mirrors. Okay, principal axis. This point at which the midpoint of this mirror at which the principal axis intersects is called the pole. Okay, it is called the pole of the mirror. Now, basically, we see that suppose there is this C here, right? There's this C here, that is, this is the center of curvature. So this distance will be the radius of curvature. Radius of curvature. Right? Next, the midpoint of this CP. So C to pole, there's this midpoint F. Right? Now this F is the focus of the concave mirror. Focus of the concave mirror. Right? Now, why do we call it the midpoint? Well, it is seen, and focus is where the point where the light rays actually meet. So it has been seen if the light rays come parallel to the principal axis, they reflect and they meet at the focus. So focus is basically the point where the parallel rays to the principal axis of a concave mirror actually meet. Right? That is called the focus. And it has been found that this focus is actually at the midpoint of CP. Midpoint of the center, the line joining the center of curvature and the pole. That is, it is at the midpoint of the radius of curvature. And the distance between the focus and the pole, distance between focus and the pole is called the focal length, denoted by small f, focal length, right? And it has been seen that focal length f is equal to what? R by 2, since the focus lies on the center of the, or in the midpoint of the radius of curvature, so the focal length will be half the radius of curvature, right? So that is the relation between focal length and radius of curvature. So it can be said that R is equal to 2f. This is again an important relation, right? Now one more thing. It has been seen that, can you see that this is the center of curvature of this concave reflecting surface, and you can see that this is the mirror. Now, it has been seen that the focus is before the mirror. It is in front of the mirror in case of concave mirror. Can you see that? So if you draw a basic structure of the concave mirror, which I'll be doing this many times. So if I draw a basic structure of a concave mirror, and suppose this is my focus, this is my center of curvature. Now, we follow a basic criterion, right, for distances in this case. And this is basically called a ray diagram. When we depict a mirror and a principal axis and light rays, this is all called a ray diagram. So we basically follow some sign conventions for ray diagrams, and this is very important that you understand this. When we move from right to the right, when we are moving to the right, we say that we have a positive distance. When we are moving to the right, we say there is a positive distance, right? And to better understand this, let us draw the Cartesian plane. Now, we all know the Cartesian plane. It is the coordinate plane that we all follow, right? So this is the y-axis and this is the x-axis. This is x dash, this is y dash. Now, we know that all these values are positive. All these values to the left are negative. All the values up are positive. And all the values down are negative, right? This is the Cartesian, basic structure. So we follow basically this Cartesian plane. When we are moving towards the right, that is the right of the y-axis, we say that we are going a positive direction, right? A positive distance. But if we move to the left, you can see if we move to the left, we have a negative distance because we are going to the negative y-axis. Hence, a distance to the left is said to be negative distance. Now, this is irrespective of concave, convex, whatever mirror you'll get. And even further, we'll be studying lenses. We follow the same convention, right? If you're moving left, we get a negative distance. Right? So that's with the left-right distance. Now, up-down distance. Now, you can judge that as well. If the body or if the object is facing upwards, right? If it's facing upwards, obviously we can see through the Cartesian plane that it is in the positive y-axis. If it is upward, if it is upright, then we say there's a positive y-axis. So distance upward is called positive distance. Right? Upward distance is always positive. When we are going up, we get a positive distance because we are moving towards the positive y-axis. And again, if we go down, we are going to the negative y-axis, so we take it as negative distance. Oh, that's absolutely clear. And this is the sign convention we follow for mirror problems and lens problems and all these things, right? This is the sign convention, right? So this is the sign convention we follow. I hope that's absolutely clear to all of you, right? Now, keeping the sign convention in mind, let us get back to our concave mirror. And I told you here that the focus is where these light rays are meeting. And you can see that they are hitting here, and then they are meeting somewhere here. You can see this is the point, and then this is the point. They are meeting at this focal point, and this focal point is to the left of the mirror. Can you see the focal point is at the left of the mirror? Right here, left of the mirror. So since it's towards the left of the mirror, the focal length, which is FP, is taken as negative for a concave mirror, because in a concave mirror, light rays are meeting towards the left of the mirror. So we say that focal length of concave mirror is always negative. Very, very important, okay? And this is important, why? Because when we are solving problems on mirrors, that's where you will find this helpful. Focal length of concave mirror is always less than 0. It is always negative. It is because the focal point of a concave mirror is to the left, all right? Left of the mirror, that is in front of the mirror. And by convention, we know that left distance is always taken negative. That is why distance from pole to focus of a concave mirror is negative. Right? This is only for concave mirror, mind you. For convex, it is different. For concave mirror, this is the case, right? So these are the basic things of a concave mirror, right? The basic things involved of a concave mirror, right? Absolutely clear with concave mirror. I hope you all are absolutely clear with that, right? So now we move on to the next kind of mirror. Now suppose let's get back to a sphere, right? The reflecting sphere. It's going to be really helpful. Now suppose the reflecting sphere has an outer reflecting surface and an inner non-reflecting surface. For example, it has an inner non-reflecting surface and an outer reflecting surface. Okay, so now you can see that here there is a non-reflecting surface inside, and outside there is a well-reflecting surface. Again, here you can see the center of curvature, radius of curvature, everything will be there. There's a center of the sphere, there is a radius of the sphere, that is the radius of curvature, and all, right? Now, we take any part of the sphere. So suppose we are taking this part of the sphere, right? This is my part of the sphere I'm taking, and this is the part I'm taking, right? So suppose, let us take this part again. Now suppose I'm taking this part here. There is a part of the sphere I've taken, and the inner part is non-reflecting, the outer part is reflecting surface, right? So you can see that if a light ray comes and it strikes, it is going to go away. If a light ray comes and strikes, it is going to again reflect, right? So now you can see here that The inner part is non-reflecting, outer part is reflecting. And it looks like the half of an X. Now you can see this is an X. So you can see this looks like half of an X, right? So such a mirror where the outer surface is reflecting, inner surface is non-reflecting is called a convex mirror. And I again remember this convex because of this X, and the X is it's half of an X. That's how I remember it, right? That's a good way. And for concave, it's cave shaped. Just remember that the reflecting surface is cave shaped. So this is what we call a convex mirror, right? Now let us take some basic ideas of the focal length and all of a convex mirror. Now suppose this is the convex mirror we are talking about, right? And suppose this is my principal axis. Now that's my imaginary line, you know that. That's my imaginary line. This is my pole. This is the midpoint of that reflecting surface. This is my, okay, leave that now. So that's my pole, right? Now when light rays come and reflect, we will see this further on in ray diagrams as well in the next video, that when a light ray comes parallel to the principal axis, it diverges. Okay, it diverges. It does not meet at a point, right? That is what is seen in the case of a convex mirror, which we will study a bit further on as well, right? Don't worry. But for now, just understand that when a light ray comes parallel to the principal axis, it diverges. So they don't really meet. But what do? Again, we apply our basic logic of human behavior, our tricky styles, and we extend our reflected rays. So it is seen that they meet at some imaginary point when they are extended. When I extend them, they meet. They don't actually meet, as in the case of a concave mirror, but they appear to meet when I extend them. So this point at which they meet is what is called the focus. And this focus here is not a real focus, it is a virtual focus. Why is it a virtual focus? It's because it is not real. Right? We have not actually seen them meet at that point. It is that they appear to meet at that point due to the extension of the reflected rays, right? So that is why we call it a virtual focus. But in the case of a concave mirror, as we have seen here, you can see that the rays appear to meet. They are actually meeting after reflection. So this focus here is a real focus. Right? But in the case of a convex mirror, there is an imaginary focus or a virtual focus, which is behind the mirror. Again, it is not in front of the mirror, it is behind the mirror. You can see that, right? So that's my virtual focus. Now you can see, suppose I want to take out the distance between the pole and the focus. So if you take out this distance, right? Again, this distance is going towards the right, right? FP, P to F is a positive distance because it is going towards the right, right? So since it is going towards the right, we say that FP, which is the focal length of the convex mirror, since it is a distance going towards the right, we say that FP is always greater than 0. We say it is a positive distance, and we say that the focal length of a convex mirror is always positive. That's it. I hope that's absolutely clear to each and every one of you. The focal length of a convex mirror is always positive because the distance is towards the right, and obviously it is a positive distance, right? So that's it with your convex mirror, right? So this is the basic overview of the spherical mirrors, and you know the basic concepts of focal length, a ray diagram, principal axis, radius of curvature, etc., etc. Right? So thank you for joining me today. This was all we had. Thank you very much. So in this video, we've discussed about the spherical mirrors, their basic components, basic ideas of spherical mirrors, right? Now in the next video, we will be starting to discuss the ray diagrams for various kinds of spherical mirrors, right? So for concave mirror, 6 ray diagrams are there. For convex mirror, there are only 2 ray diagrams. So we will be discussing them in 2 different videos. Thank you very much for joining me today. Goodbye. Stay healthy, stay smart. Do like and subscribe. Bye bye, and do keep studying.